Well, hello again. Welcome to Lesson 2 in our Introduction to Probability unit. Today we're going to put together some things that you've been learning over the previous 2 units in permutations and combinations. And we're going to show you how to calculate probabilities using the counting techniques that you're now familiar with. So in many situations, possible outcomes are not easy or convenient to count individually. In these cases, the counting techniques that we've learned will be really helpful for calculating the theoretical probabilities. That's a big yay. So let's recall that the probability of any event, now you can define it, can be probability of E or probability of D or probability of F, like whatever makes sense to you, is the number of ways that event can happen over the total number of outcomes in the sample space. And again, that is usually the way you would calculate without any restrictions. So your denominator is the no restrictions value that you've been calculating all along. Probabilities exist between 0 and 1, including 0 and 1 if you're definitely not going to happen or 100% certain. Any other values don't have any meaning. And recall that if you have a probability of an event that you don't want, well, 1 minus that will get you the probability of the event that you do want. So we can use the complement. Now, we've been referring to it as an indirect method, but here, now that we know that all the probabilities will always add to 1, we just say that it's the complement. And then there's your E and E prime. Okay? Just a quick little review.
All right, so let's go over a few examples when we have permutations, and when we're going to use permutations. This is when order does matter, right? So when time order or when spatial order is important. So here's Alphonse and Beauregard. They enter a race with 5 friends. So it's 7 people in the race. The racers draw straws or draw lots to determine their starting positions. What is the probability that Alphonse will start the race in lane 1 and Beauregard will start the race in lane 2? So when we talk about ordering these couple of friends, there's a couple of things that we have to think about. First, we need to say that the event, we're defining our event E as the event of Alphonse in lane 1 and Beauregard in lane 2. So how many ways can A be in lane 1 and Beauregard be in lane 2? And all of a sudden we come to a very familiar permutation problem.
Sure, let's just put Alphonse in lane 1.
So here we're going to remind, so this is what we're looking for. We're looking for the number of ways that this event can happen. So let's put Alphonse in lane 1. Let's put Beauregard in lane 2.
And there's one of each of those.
Yeah, so we don't have a choice there. So how many students do we have left over? Well, we've got 5, and we've got 5 spaces to fill. So that would be 5 factorial ways. And there are 120 different positions where Alphonse can be in the first lane and Beauregard can be in the second. Well, if we want to find the probability, what we need to do is now we need to locate, okay, how many total different outcomes do we have?
Without any restrictions.
Without any restrictions. So in how many ways can the race be finished, or in how many ways can the race be started, and how many ways can you order 7 people in a line?
7 people, 7 spots.
7 factorial.
7 factorial, yeah.
So there's 5,040 different ways that these 7 people can be lined up into these 7 spots. And so we say, okay, well, let's figure out the probability. We have 120 ways where these 2 guys are in the first and second position. That meets our restriction. And we have 5,040 ways where we can order the 7 of them in any random order. So 120 over 5,040 is 0.023 or 2.3%.
Yeah, absolutely. All right, let's look at a different example. We've got a bag. It has 26 tiles, each one marked with a different letter of the alphabet. What is the probability that Simon will take out 4 consecutive letters, so 1, 2, 3, 4, and not replace them and have them spell out the word math, M-A-T-H, in that order?
So you have to be thinking, holy cow.
Oh my gosh, right? So we've got 4 spots to fill. There's only 1 M, there's only 1 A, there's only 1 T, there's only 1 H, right? So if we're looking at the event of pulling M-A-T-H in that order, then it's just going to be 1 times 1 times 1 times 1. There's only
one way that you could pull out an M,
Earth.
and then an A, and then a T, and then an H. So there's only one way of doing that. And so we set the number of ways that we can pull the word M-A-T-H in that order is 1. However, now what do we have for all the remaining letters?
Well, now we've got, 26 tiles, and we want to pull out 4 letters out of that 26. And so we think, okay, well, we've got 26 tiles, we've got 4 letters. We want to know the number of ways that you can just take 4 letters out of 26. But remember here that we're not just grabbing 4 and we don't care. what order they're in.
We do care what order.
We do care because we're pulling them out first, then second, then third, then fourth. So really, we've got 4 spots, and instead of 1 times 1 times 1 times 1, we're going to do 26 times 25 times 24 times 23, or 26p4, and that's going to be the number in our sample space. So if we want to know, all right, now what's the probability of pulling MATH in that order? Well, we know the number of ways that can happen is 1, and we know the total number in the sample space is 358,800.
That's
so
a tiny
that's
probability.
a really small probability.
And we could have guessed that. You know, if you got a bag with 26 tiles in it, and you want to pull out MATH, that's going to be a tiny probability of doing that.
The world is against you if you're striving to do this. We're sorry.
Okay, so now we've looked at combinations. Excuse me, we've looked at permutations. Now let's investigate a couple of examples with combinations. Here, order is irrelevant. So we're just choosing or grabbing some items. All right, so one of the very archetypal questions in this is marbles, and drawing marbles or drawing candies or choosing something out of a bag.
Yeah.
Okay, so suppose that Samantha randomly draws 2 marbles, and she's not going to replace them. All right, so she's going to take one, and then she's going to take the other from a bag containing 6 green marbles, 4 red marbles, and 3 blue marbles. Yeah. So let's determine the probability that the 2 that she's going to pull out are going to be red.
Okay, so she's going to reach in, she's going to close her eyes, she's going to feel around. Now, because they've said 2 marbles without replacement, you can think of it as pulling one and then pulling the other.
Yeah.
Or you can just think of it as reaching in and feeling for 2, and then just plucking the 2 of them out simultaneously, right? So however you want to think about it, either way, we've got piles of marbles. We've got a red pile, we've got a green pile, and we've got a blue pile.
Yeah.
And we're saying, what's the probability that you're going to pull both of them will be red? Yeah. And so
here we go. Yeah. So basically, the event, just as you've been explaining, is that the event that both marbles are red.
Yeah.
So we need to figure out, of course, the number of ways that this can happen, i.e. combinations.
Yeah.
And then the number of ways that we can just pull any 2 marbles.
Any 2 marbles from all those marbles.
Yeah. Yeah. So we have 4 red marbles to choose from. The way that we could pull 2 of them is 4 choose 2.
Yep. So from the pile of red, we're choosing 2 of them. So we're taking 4 choose 2, which gives you 6. But, I mean, how many marbles do we have all together here?
13.
13.
So 6 plus 4 plus 3 is 13 marbles.
Throw them all in a pile, stir them up, and just pull out any old 2. That's our without any restrictions.
Yeah.
That would be like a part A type question. So our sample space is just 13 choose 2, which is 78. So then the probability that both marbles are red, the probability of event E, is just 6 over 78.
Okay.
Yeah.
So here we have basically a 1 in 13 chance.
Yeah.
Determine the probability that she picks at least 1 green. Holy cow, we're talking about at least. All of a sudden we think, oh.
Cases.
Either cases, or we could use an indirect method, or maybe the complement. Yeah. So really, the probability that she picks at least 1 green means that we're looking for the probability that she doesn't choose
no greens.
No greens. Like we just don't want no greens. We want at least 1 green.
One
so
green
1 or 2.
2 green would be good. No green is the only unacceptable.
So let's say that E is the event of no green marbles. Okay? Which is a little bit different because this is what we don't want to have happen.
Yeah.
And so what we're going to say then is that the number of ways that we can choose no green marbles is, okay, well here's our 6 green and we're going to choose 0 of them. Here's our 7 other marbles, and we're going to choose 2.
Yeah. Now we've tossed the 4 red and the 3 blue together.
Yeah.
Because we don't care whether it's red or blue. We just care that it's not green.
Yeah.
So notice how now instead of 3 piles, we've just said the green pile and the not green pile.
Yeah.
So that's why it's 6 and 7.
Yeah. And then here we have the number, again, the number of ways that we can just choose any 2 marbles. This is like the no restriction case. And we've got 13 marbles, and we're going to choose 2 of them. So enter the complement. The probability of not choosing a green marble is 21 and 7/8.
Yeah.
It's 21 and 78.
Yep.
We'll use this notation here and we'll say, hey, the probability of not choosing a green marble is equal to 1 minus the probability of choosing at least, excuse me.
Backwards.
I got that backwards. The probability of choosing at least 1 green marble.
Yeah, 1 or 2.
Is equal to 1 minus the probability of no green marbles.
There we go.
Okay, so it's 1 minus 21 and 78, and if you work this out, we get 57 over 78. Yeah. So 73% chance that we're going to pick at least 1 green marble.
Sure, because there's more greens than anything else.
All right. So one of the final questions here: a focus group of a focus group of 3 members is to be randomly selected from a medical team consisting of 5 doctors and 7 technicians.
Okay, so if we think of what we're looking at here, we've got a group of 5 doctors, we've got a group of 7 technicians. You know, essentially that's 2 piles of people, the doctor pile and technician pile. All together they make 12 people, and we want to somehow select 3 members. So just sort of wrap your head around this scenario first, and then we can start asking ourselves, okay, what is the probability that the focus group will be comprised entirely of doctors? So I want to know, what's the probability of event E being all doctors? So we'll sort of define event E as the event that you just have 100% doctors. If you have 100% doctors, then you don't have any technicians.
Yep.
So then if you've got your 2 piles, your doctor pile and your technician pile, then I want all 3 to come from the doctor pile and none to come from the technician pile. Note again that the N choose R notation here, the 2 N's, the 5 and the 7, would add to 12, and the 2 R's, the 3 and the 0, would add to 3.
Yep.
So we're still doing the same kind of thing that we were doing with cards last unit, where you've got 2 piles and the N's and R's should add up. So there's 10 ways of having all doctors, but that's not a probability. We need a denominator. We need the sample space. And again, if we just toss all 12 people together and we don't care what we get, then no restrictions. The sample space is just 12 choose 3, which is 220.
And the probability of this is just NE over NS, which is 10 and 220, which is 0.045.
Yep. And notice we use E all the time right now because we're just doing one event at a time. Each question is different.
Yeah.
But once you start combining probabilities, you'll start using other letters that might make sense to you in the situation.
And we could even say, you know, the thing is that because we don't want to keep on writing this. We don't want to write P bracket event of all doctors.
Right.
Like we don't want to write that. So we just shorten it to one letter, right? But we could say the probability of all D, you know, or we could say the probability of D, or we could say, you know, like we could do that. We could throw that in here. Really, we're trying to minimize the amount of writing that we're doing.
Exactly. Yep.
So what's the probability that the focus group will not be comprised entirely of doctors?
Well, I mean, if you picture that sort of mini Venn diagram, and if the smaller set E is, it's all doctors, then everything else is not doctors, like not entirely doctors, so at least some technicians on there.
Yeah.
So again, we're going to use the complement, and we're still taking E as the event of all doctors. So this time we actually want to find probability of E prime. So we're going to take 1 minus the probability of E, 1 minus 10 over 220, 210 over 220, about 95%. So the probability of not getting all doctors is about 95%. Yeah.
So now we can figure out the probability that the group will be made up of exactly 1 doctor and 2 technicians.
Yep.
So again, we're going to revisit something up here that we did before, but instead of having a 0 down here, because this is the case where we had no technicians, we're going to say, okay, exactly 1 doctor, exactly 2 technicians. So E is the event of 1 doctor and 2 techs.
Yep.
And so the number of ways that this can happen is, here's our doctor pile, 5 choose 1. Here's our technician pile, 7 choose 2, because we want 1 doctor, bing, 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 and then we want 2 technicians, bing, 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 bing.
And notice the word and.
And the words and, so we're multiplying these together. So 5 choose 1 times 7 choose 2 is 105.
There we go.
The number of ways, of course, that we could choose 3 people from a group of 12 is our denominator, and that's just 12 choose 3, so we get the same 220, and the probability of this happening is 105 over 220, so 47.7%. The group will be made up of 1 doctor and 2 technicians.
Yep.
All right, our last game, our last lesson in the unit, in the lesson is, of course, example number 5. And this is about poker, okay? So in the game of poker, each player is dealt a 5-card hand, okay? So you're going to be dealt 5 cards in your hand. The deck has 52 cards in it.
Okay. And again, once it's in my hand, I don't care what order it is. I'm going to reshuffle in my hand and organize it how I want. So we
this
know
is
we're
definitely
dealing with combinations.
Combinations.
Yeah.
So let's find the probability of receiving a hand that contains a spade flush. So a hand that contains all 5 cards and they're all spades.
Okay.
Okay.
Yeah.
So basically, E is the event of all cards spades.
Yeah.
And what we could say is, okay, well, the number of ways that can happen is we have 13 spades to choose from, and we're going to take 5 of them. So we got 13 choose 5.
You got it. Now you could imagine here, if you want to add this in for yourself in your own notes, if this is the way you like to think about it, that you've taken this deck of 52 and split it into 2 piles. the spade pile, of which there are 13, and the not spade pile, of which there are 39. And you can imagine you've done 13 choose 5 times 39 choose 0. So you're taking like all 5 spades and none of the other 39. We haven't added that in because anything choose 0 is equal to 1. There's always one way of choosing nothing. And so this is really 13 choose 5 times 1, kind of. But if it helps you to think of the two piles and to account for both piles, then that's what the other value would be in that product.
So then we need to figure out the total number of hands that are possible, the total number of five card hands that are possible.
Without restrictions.
Without restrictions. So we got 52 and we're going to choose 5 of them. So, and that's NS, right? So 52 choose 5. And we looked at this before. There's actually 2,598,960 unique poker hands. And so the probability of getting an all spade flush is 1287 divided by 2598960. And if you work out this in a percent form, this is 0.049%. So, you know, we're talking a tiny fraction of a percent in getting a spade flush. So let's find the probability of receiving a hand containing a full house, which would be 3 kings and 2 5s. A full house, and exactly this, right? Exactly 3 kings and 2 5s. And let's figure out the probability of this. Well, E we're going to set as our event of 3 kings and 2 5s.
Yep.
Okay.
And we want to now separate the deck out into piles. There's going to be a king pile, there's going to be a 5 pile, and then there's going to be the pile that's neither kings nor 5s, of which we're choosing none. So we don't actually have to write that pile down. But there's 4 kings, there's 4 5s, we're choosing 3 of the 4 kings, we're choosing 2 of the 4 5s, and we're choosing both of them, so we multiply, and we get 24 different ways to have 3 kings and 2 5s.
Exactly. Okay. So again, the number of total poker hands would be 52 choose 5, and we get 2,598,960. And the probability,
really
holy cow, that's really tiny. If you work it out, it's 9.23 times 10 to the minus 4%.
Break out the scientific notation for this one.
Yeah, because it's such a tiny percent.
Or you can leave it as a fraction. That's okay too.
Yeah, you can leave it as a fraction as well. So there's a couple of examples of permutations and combinations. Your homework is, of course, at the bottom of your note. And the questions range from being, you know, pretty straightforward to, you know, really requiring a lot of thought.
A lot of thinking.